All right. So let's first talk about what's left. What's left? There is exam 4 a week from today. And that's going to cover everything from the whole semester. The last I'm going to talk about this new topic is Friday. So Monday we'll just do review and stuff. So it's going to be everything through the whole course up through what we do on Friday. And then we have makeup exam. I haven't looked at when our final is scheduled. Is it anybody looked at that? Okay, that's what I was thinking. So yeah, I think it's 8 a.m. on Friday. Last day, earliest test. Great. I think that's true, but and the way that works, that makeup exam is just going to be, you can think of it as basically a new version of exam 4, but you can use it to replace any one of your previous exams. So if you have a score that you think you can, do better on with a cumulative test, take the makeup exam and it'll replace your lowest score. Yep.
Is there any risk to it?
No risk, right. So if you score lower than other exams, then I'll just keep the higher. And I'll get exam 4 graded by Friday night, so I guess think by Friday night until I go to sleep. So by Saturday morning, you can get up and see how you did on exam 4, and it can also replace the score on exam 4. Okay? And you might ask if it's another version of exam 4. Okay, so if you're still trying to process how complicated all the rest of this stuff was, you don't have to think about this. But if you got all this and you're thinking, if this is a new version of exam 4, how come I can't just use exam 4 to replace one of the first 3 exam scores? I'll do that too if you want. If you want to not take the makeup and you have a bad score from exam 2 and a better score on exam 4, I'll make that switch if you don't take the makeup. You know what I mean? You know what I mean? Okay, yeah. It's a much simpler idea than it sounds in words.
So basically you keep the exam 4 and the exam 4 grade gets replaced with whatever.
You keep exam 4 because that's your exam 4. But then since that's the same kind of test as the makeup that's going to be the next week, if you don't want to take the makeup, then I'll just so say you got a 12 on exam 2 and a 20 on exam 4. Then if you don't take the makeup the next week, you want to just be done with tests after exam 4, I'll give you the 20 for exam 4, replace the 12 with the 20 for exam 2, and you're done for the semester with exams.
So you jump tests that can replace 2 other tests. Do you have exam 4 and the makeup one?
Right. No, you
It's just one or the other?
it's just one or the other to replace a test.
So the only reason that you would take the makeup exam is if you don't do well in exam 4?
I guess that's true, yes.
Okay.
That's a good way to think about it, yes. That's right.
But will you have exam 4 graded early enough for us to see if we should take the makeup exam or not?
So yes, by Saturday morning, when you wake up, unless you wake up in the middle of the night,
Not his problem.
then exam 4 grades will be posted. I'll do a review.
Oh, okay.
And I'll answer questions and stuff. I guess really, yeah. Maybe let's. I haven't thought that far ahead yet, but maybe let's just do questions. So if you have questions, come. Yes.
Is the exam 4 the same as like are you doing that same thing in statics? Or is it just
Yes.
Okay.
Same thing in statics. It's 513. And then there's a third problem set. It's not really a problem set, but you have to turn it in. And here's all it is. Everybody should get full credit on this. Just put a little time into it because it'll help you get ready for the test, and it'll help you retain stuff after the class is over. It's an outline of the class. With all significant equations. There's some leeway on what you think is significant, I guess, but for the most part, all the equations that I box in the notes, with those inserted in the, correct place. And that is due by 11:59 p.m. Sunday, what would that be? 6, 7, 8, 5, 8? Okay. I believe that's all. Any questions about that? We're not going to do a quiz on Friday, just so we're done with quizzes at this point. So I can, because all the material on exam 4 is going to be the stuff that's covered up through Friday, so we're just going to spend the full day Friday. I don't curve anything individually. I just curve the final score if I need to, the final grade percentages if I need to. Any other questions? All right. Well, I need to make a correction to a sign error that I gave you last time. And I want to explain, I think understanding how I made this mistake will actually be sort of helpful, so I want to sort of be clear about it. So first, let me just give you the corrected version. So when you're doing the moment of inertia matrix about a point that's not the center of mass of the object, it should be the moment of inertia matrix about the center of mass plus this parallel axis theorem matrix, and all the values are correct. This is what I gave you last time. So all these values are right. this should be, so last time I gave you this as positive. All of these were positive. That's the problem. So x bar, z bar, m, y bar, z bar, and then this one is m, x bar squared plus y bar squared. And all of the product of inertia parallel axis theorem parts should be negative. So all the off diagonal elements should be negative. And the reason that's an easy mistake to make is because the way it works is like this. The moment of inertia of A, like let's say xy element, is equal to the moment of inertia, the product of inertia about the center of mass, xy element, plus m x bar, y bar. Okay, so it's plus there. That's true of all those products of inertia. But then the moment of inertia matrix is equal to this matrix with all the products of inertia negative. Okay, so you end up, so do you see what's going on there? You end up subtracting that parallel axis theorem part 2 in the matrix. And so if you think of this as adding on a parallel axis theorem matrix, all those elements have to be negative. Okay, so let me revisit that example from last time. We had so we had this coordinate system with the origin at A, and this coordinate system with the origin at the center of mass. They're oriented in the same way. And this vector is x bar, y bar, z bar. So the moment of inertia about the center of mass was given, and that was 5, negative 1, 0, negative 1, 2, 2, 0, 2, 3. Okay, that's given. And we want to calculate the moment of inertia matrix about A. Well, this vector was given as 0.5, 1, negative 0.2. And also the mass was given as 1 kilogram. So the moment of inertia matrix for the whole thing at the origin A is equal to the moment of inertia about the center of mass, plus this matrix, m times the quantity y bar squared plus z bar squared, negative m x bar y bar, negative m x bar z bar, negative m x bar y bar, m times the quantity x bar squared plus z bar squared, negative m y bar z bar, and then you get 2 here from symmetry. And then the z element, diagonal element, is m times the quantity x bar squared plus y bar squared. So that is 5, negative 1, 0, negative 1, 2, 2, 0, 2, 3, plus, if you calculate these, you get 1.04, negative 0.5, positive 0.1, then negative 0.5, positive 0.29, positive 0.2, positive 0.1, positive 0.2, 1.25. And so add those together, you get 6.04, negative 1.5, positive 0.1, negative 1.5, positive 2.29, 2.2, positive 0.1, 2.2, and 4.25. All right, any questions about that? So let's do a deluxe example where we have to deal with both of these two things. So let's say we have a setup like this. There's a disc rotating on this angled arm. Where the coordinate system is oriented like this. So this is supposed to be parallel to the y-axis. Can you see what I'm trying to get at there? That vertical one is parallel to the y-axis. These are supposed to be perpendicular. This distance is 0.2. This distance is 0.3, 0.32. And the mass of the disk, this will come up, oh no, this will come up now, 8 kilograms. And the radius of the disk is 0.1 meters.
Is that 0.2 going to the radius or to the envelope?
That's going to the center. And we want to calculate the moment of inertia matrix about the center of the disk, so that's A. And then we want to calculate the moment of inertia matrix about B up here. Okay, so for part A, the disk looks like that. The coordinate system looks like this. And so the moment of inertia about the center of mass, I guess I was calling it A. What's the moment of inertia of this disk about the x-axis? Or what's the formula, first of all? That's for a slender rod. Yeah, 1/4 mr squared. And these are the principal coordinate axes, so we don't have any products of inertia. What about the y-axis? What's the moment of inertia for the y-axis? 1/4 again. And then the different one is the z-axis. What's that? Yep. And so plug all those values in and you get 0.0200, 0.020, and then 0.04. And this is in kilogram meters squared. So that's it for the moment of inertia about the center of mass. Now we want to calculate the moment of inertia about B. So that's equal to the moment of inertia about the center of mass plus the mass times the quantity, mass times the quantity y bar squared plus z bar squared, negative mass times x bar y bar, negative mass times x bar z bar, negative mass times x bar y bar, mass times the quantity x bar squared plus z bar squared, negative m y bar z bar, negative m x bar z bar, negative m y bar z bar, and then the last one is m times the quantity x bar squared plus y bar squared. Okay, so let's figure out what these quantities are. So what's the value of x bar? Do you remember what that means?
Negative 1.32.
We're going from the point of interest to the center of mass. So you're thinking about it right, but you have the wrong direction. So it's positive 0.32. Okay? What's y bar? Negative 0.2. And what's z bar? 0. Yep. And so this matrix is equal to what did I say for the mass? So 8 times 0.2 squared plus 0 squared. Then this one is 8 times, or negative 8 times 0.32 times negative 0.2. This one's 0. Anything that has a z-bar in it is going to be 0. This one, because of symmetry, is negative 8 times 0.32 times negative 0.2. The y element is 8 times 0.32 squared plus 0 squared. This one has a z-bar, is multiplied by a z-bar, so that's 0. And so we have 0, 0, and then 8 times the quantity 0.32 squared plus 0.2 squared. And if you multiply all those out and then add the two matrices together, I think you get 0.34, 0.512, 0, 0.512, negative 0.8392, that doesn't make any sense. What's 8 times 0.32 squared plus 0 squared? What? 0.8192. And then we're adding that to 0.02, so it's just positive of this. Those diagonal elements always have to be positive. Yep. Top left. Oh, and then that's added to, yeah, that's added to 0.02 because we already have that from the first part of the example. And then 0, 0, 0, 1.1792. Okay, so now, what if we wanted our coordinate system to keep the same z-axis, but be rotated 45 degrees about the z-axis. So part C, what's the moment of inertia matrix about B for the green axes? Well, the rotation matrix Q is, that's a positive 45 degree rotation about the z-axis. So that's cosine of 45, sine of 45, 0, negative sine of 45, cosine of 45, 0, and then 0, 0, 1. So you have 0.7071, 0.7071, 0. Then negative 0.7071, 0.7071, 0, 0, 0, 1. So now we can take this matrix in our old coordinate system axes and calculate the moment of inertia about B in the green axes. Let's call this black. Is equal to Q times the moment of inertia B with the black axes times Q transpose. And anybody, can someone multiply that? One point what? 1016. 0.2. Oh wait. Did I get off one element, or is that right? This is your x?
Yep.
Okay, and this is your y? So, okay, so 0.2 what? 496. Okay. Okay. Point oh what? 776. 0. 0.1. Oh, 1.1792. Okay. Anybody have any questions about that?
What is the, okay, so you have the Q and then the QT, what are the differences between them?
The transpose of a matrix is, so if you have this matrix transpose, it means you switch what were rows are now columns, and what were columns are now rows. So the first row in this one is AB. In its transpose, that's the first column. So this row is now this column. And CD, that was the second row. Now that's the second column. Any other questions? Okay, so now we can use this to calculate angular momentums. The angular momentum of a body, and for us we're talking about rigid bodies, can be calculated about any point. But it's especially easy about 2 points. And what do you think those 2 points probably are?
Center of mass and
Exactly. Center of mass and fixed point. Yep. That's a point that's at rest in some inertial coordinate system. And that's good news, because those are the most important ones for our calculations, because we know for rotational Newton's second law, those are the 2 key points that we want to deal with. So those are also the two most important cases. Okay, so the angular momentum h is a vector. And it's equal to the moment of inertia matrix times the angular velocity vector, where A is the center of mass of the body or fixed in an inertial coordinate system. Okay, so let's go back to the example, the last example we did. So we had, what? Yeah. So we're just going to calculate angular momentum for that system that we had in the last example. And this time we're going to give rotations. So all the lengths are the same, the masses are the same. But now this disk is rotating this way at 12 radians per second. And the arm is rotating this way at 4 radians per second. This is the point A, and this is the point B. We want to calculate the angular momentum of the disk about A, and B, the angular momentum of the disk about B. Does anything change for angular momentum when we go from point to point? Was that a shrug? Okay. No, it doesn't. So in the, like, notice in all these formulas we use, we have for our moments, now for our angular momentum, for our moments of inertia, we're always talking about rotations about a point. Angular momentum, angular velocity and angular acceleration are not that way. Those are just pure quantities. They're true for every point on the body. There's no such thing as an about point for how an object's rotation is changing. Okay. So what's the angular velocity here? Calculate that just by summing the two. So we have, so if our coordinate axes are like this, x, y, z, then we have a rotation of positive 12 about the z-axis, and we have a rotation of +4 about the y-axis. And so the angular velocity is just equal to 0, 4, 12 radians per second. And that doesn't change, you know, so that's what we're going to use for parts A and for part B. So for part A, the angular momentum about A is equal to whatever we got for that last. So that's going to be equal to 0.0200, 0.020, 0.04. Times 0.412. Could someone calculate that? Okay, and that is in sort of funny units. What are the units here? So we got kilogram, meters squared, radians per second. So that's kilogram meters squared over seconds. One thing that might be a little surprising with this angular momentum is, in general, and this is an example of it, there's no reason that the angular velocity and angular momentum have to be in the same direction. With linear momentum, that wasn't true, right? They're always in the same direction. But here, these two vectors are not parallel to each other. Okay, then the second one, the angular momentum about B. We had this thing. And we're multiplying that by the same angular velocity, so 0, 4, 12. And can someone calculate that one?
Why are we using the matrix for?
It's the rotated matrix.
Okay.
That's the rotated one? That's not the rotated one, right?
That's the right one.
Yeah. Sorry. I'm looking at
Okay. Okay.
3.357
Okay.
and 14.15.
14.15 kilogram meters squared over seconds. Anybody have any questions about that one? Okay, so now if you wanted to do, if you wanted to express that in a rotated coordinate system, you could use a rotation matrix to re-express this vector in the new coordinate system. Or you could use that rotated mass moment of inertia that we had before and calculate it that way, and they need to match. So the next thing we're going to do, the last thing we're going to do next time, is we're going to use this new form of the rotational Newton's second law that says the sum of the moments about a point A is equal to the time derivative of the angular momentum about A for A that's either the center of mass of the body or second, a fixed point. And we are going to have, we'll have our coordinate system rotating with the body so that our I matrix is constant. And therefore, this is going to take the form that comes from taking time derivatives in rotating coordinate systems, that HA dot is equal to the components dot plus the angular velocity of the coordinate system crossed with the angular momentum. Okay, so that's what we'll do next time.